Hi everyone, my name is Steve. Today we're going to talk about insertion sort, which is one of the most basic and useful in a lot of cases. It might not be the most efficient and not the most commonly used one, but it's a very good introductory sorting algorithm to help people understand, get the basics sorted out in computer science. So with that said, let's dive into this insertion sort. Basically, insertion sort, we can picture that as, like say, you are given a handful of cards. So suppose we are given these 5 cards and labeled as 3, 1, 4, 5, 2. We'll just picture that these 5 cards are just placed face down on the desk. And then we'll just pick one of them in order and put them into a pile with sorted order. How can we do that? Let's take a look. So the first one is going to be 3. So we'll just remove 3 from the desk and put it into the first place of this sorted queue. Second, we'll take 1. But for 1, because 1 is smaller than 3, so 3 is taking the first position. So we have to move 3 to the second position and place 1 into the first position because we need to sort them in the correct order, ascending order. Now we have moved 3 and 1, so now we'll take 4. 4 out of this queue, we'll put 4. So 4 is greater than 3. So in this position, we don't need to do anything. We'll just put 4 into this correct position. It's still in ascending sorted order. Next, we'll take 5. 5 into out of this queue and put into this queue. 5 is greater than the last sorted element. So we can just safely put 5 into the correct position, which is just to append into the current queue. And then we get 2. So we'll take 2 out of the original desk and then we'll compare from the very last one. 2 is smaller than 5. What are we going to do? Since we need to put them into sorted order, so 5 needs to be moved towards right. So 5 is moved towards right. This is one movement. And then we'll keep going on until we find a position where this element is not greater than this current key position. So we'll keep comparing, keep moving towards the left, from right towards the left. So next one is 4. So 4 is still greater than 2. What are we going to do? We'll do the same. We'll move 4 towards the right. And then we'll keep going on. So next one is 3. We'll compare 2 and 3. So 3 is still greater than 2. We'll continue to move 3 towards the right. And then at this position, we found 1 is not greater than 2. So we'll just safely put 2 in here. Now we have everything in the correct position. That's a basic glimpse of how insertion works. So now let's put them into the actual code. The actual code goes like this. So we'll just have a simple method API. A signature looks like this. We'll use Java to do this. This is not pseudocode. This is real code. Because I feel the real Java code is actually easier and more straightforward than pseudocode. Of course, you can pseudocode could be generalized. You can use pseudocode for Python programmers, for CPP programmers, or for Ruby programmers, but I'm a very Java guy, so I feel this Java implementation is much more straightforward than a pseudocode. So just bear with me, we'll just use the Java code to go through this insertion sort algorithm. So suppose we're still given this original input array. What's next? Next is, so our next step is that from the very beginning, we'll start from the second index, which is in computer science, it's j equals to I, because every index, every array everything starts from 0 in computer science. We start from this one until we reach the end of the array. So this is the current card. Remember, in the previous example, we're just taking cards off of the table and put them in the correct position of the sorted array. So suppose this is the one that we are constantly taking. J is the current card we are taking from the table and trying to insert this current card into the sorted order. Next, we'll have a constant variable. We'll just call it key. Key is going to help us hold this array because this one might be overwritten. Next, we'll have another variable which is on the left side. We'll start from j minus 1. So j minus 1 is we'll use another variable called I to stand for that. While, remember, we move from the right towards the left, there is a sub-sorted array on this side. Will keep moving until when? Until I is smaller than 0. Then we'll just break out. That means we have gone on this side. There is no other elements that we can iterate on that we need to compare. And also, what we need to check is the array I, which is this one. It needs to be greater than this key element, the current one that we are trying to insert into the sorted correct order. Only if these both conditions are met, we'll do the things that we need to do in the while loop, which is to keep switching, move all of the elements that are greater than the current key elements towards the right, because everything here on this side has been sorted in the correct ascending order. So we'll just keep moving everything towards right, one step toward the right. So what we're going to do is, this is taking the current I position, which is this one, and assign this one to the next one, which is here, right? So we'll move, right now I is pointing, I is 0. So we'll start from the very beginning. I is 0 because j equals to 1, j minus 1 is 0. So I is 0, I 0. So array 0 is 3, so we'll assign 3 to this position. This position is 1, but that's fine. We're overwriting 1. Yes, we're overwriting that, but that's totally fine. We're not losing the value of this element because we had a temporary variable called key, right? We have a temporary variable called key that is holding the value of this position. That was originally in this position is 1. So we're overwriting this. We use 3. We always use the one on the left to override the one on the right next to it. That means we are moving this one towards the right. So we put 3 here. Next step, we'll decrement I. Remember we said in the quick intro that we just talked about, we keep moving one index from the right, keep moving it towards the right, moving towards the right. At this point, we need to decrement I by 1. So I was 0, so decrement by 1, it becomes 0. Okay, and then next we need to assign this original key. It is 1 here. We need to assign it to I plus 1. For example, at this position, I is minus 1. I minus 1 plus 1 becomes 0. So I plus 1 is 0. So we assign key 1 to here. That's why this one becomes 1. So we'll just keep doing this. This is a for loop. Outside of this while loop, this while loop is to move everything in the sorted sublist towards the right if it's smaller than the current key element. And the for loop in the outside is this j. This one helps us to keep track of all of the elements in the original unsorted array that we need to work on. So j at this point, this one is finished executing. Now it will continue to go to this for loop, j++. Now j++, j was 1, so j++ becomes 2. 0, 1, 2, j is here. Next, we continue to use this temporary variable key. We hold the original value at j's position, which is 4. Now we instantiate the temporary variable I becomes 1. And then we compare I is greater than or equal to 0, that's correct. And then array I is what? Array I is 3. 3 is 3 greater than key 4? No, it's not. So it's not going to come into this while loop. Instead, we'll just put it here. We execute this, it doesn't change anything because I plus 1 is key already. So 4 is here, is correct. Now we keep incrementing j. J becomes at this position 0, 1, 2, 3. So j 2 plus 1, it becomes 3 at this position. And then we have key is 5. We hold the original value that was at this position. And then we instantiate I becomes j minus 1, which is 2. 0, 1, 2 here. Now we continue to check if array I is 4. Is 4 greater than key 5? No, it's not. So we're not going to enter this while loop. And we'll just execute this, which doesn't change anything. Okay, then we continue. Now j is incremented by 1 and I is here. Now we'll continue to check here. Array I is 5. Is 5 greater than the key, which is 2? So what are we going to do? We're going to enter this while loop, which is to move everything here to the right. Okay, it's going to happen. First, it executes this, which, as I said, it's moving this one, the one on the left, assigned towards the right. Basically moving everything, shift all of the numbers towards the right by 1. And we don't need to worry about the original value at this position. We have a temporary variable holding the original value here. Next, I decrement by 1. So I is moved here. Then here we'll check the while loop. Does the while loop condition still hold? Is that the case? Yes, because array I is 4. 4 is still then key 2. Okay, so we'll continue shift. This one, again, we shift 4 towards this position. And then decrement I. I becomes here. So array I is 3. 3 is still greater than 2. What are we going to do? Again, we'll shift 3 towards the right. Now we have 3 here. Then we will continue to decrement I. I becomes 0. So array I is 1. Is 1 greater than 2? No, it's not. So this condition doesn't hold anymore. So we'll break out. Then we execute this line. This line assigns key, which is 2, to I plus 1. I plus 1, I is here, plus 1 is here. So we assign 2 here, then we're done, right? All of this is in correct order. Now we just return this array. Notice a couple of things. We didn't create an extra array, right? We are still using, everything is in memory. We are still using this original input array. That's why this insertion sort comes with a nice feature, which we're going to talk about in just a second. This is the entire walkthrough by using this very straightforward Java solution. I hope it makes sense to you guys. Now let's move on. What's the space complexity of this insertion sort algorithm? By space complexity, we're always talking about, is there any extra memory that we require in order to perform this algorithm? We don't talk about the original input because that's something it's always there. For example, this one, it could be like 1 million numbers, right? In memory, it's always there. We're talking about the extra memory that we require, we need to use in order to perform, to run this algorithm. What's the magnitude of the space complexity? That is constant. Why? Because we are only using a constant variable. That is the key. Done. We never initialized an extra array or an extra data structure to do this, right? Also, this is known as in-place algorithm. This insertion sort is called in-place. Why is it in-place? Because you see, we keep shifting things towards the right. We are not initializing any extra memory or any extra data structures to do this, to implement, to finish this algorithm, this sorting process, right? Also, another nice feature of insertion sort, not every sorting algorithm comes with this nice feature, which is stable. By stable, what does stable sorting algorithm mean? That means it doesn't change the relative order of elements with equal keys. So suppose there are 2 1s or 2 3s in the original input. 1 3 is here, 1 3 is here. After applying this insertion sort algorithm, the original 3 3, they are still in the relative order. So their order doesn't change. Why is that? Because we keep shifting things from the right towards the left. So we keep shifting things on the right first. We move this one here, then move this one here, then move this one here. So the relative order could be kept after applying insertion sort. So this is another cool, nice feature of insertion sort, which is called stable. Now let's talk about the time complexity of insertion sort. The best case is that an array is already sorted. That is ON, because we still need to check for every single element. We need to compare it at least once, right? For example, here, this one, we need to compare 2 with the last sorted biggest element, which is 1. And this 3, we need to compare with the last sorted biggest element, which is 2. So anyway, we need to compare every single element at least once. So the best case is that an array is already sorted. So that is ON. What's the worst case? The worst case is that an array is sorted in completely reverse order. For example, this 5, 4, 3, 2, 1. It's completely sorted in reverse order. In this case, it's going to be ON squared. And what's the average case? The average case is still ON squared. So insertion sort doesn't really appear in your practical work too much because there are more advanced sorting algorithms, for example, quicksort and merge sort, which are much more efficient when handling large amount of input. Like say there's 1 million numbers that need to be sorted, which is very common in computer science, especially in these large technology companies. Just suppose the data, the customer, the volume that they are handling. So it's very common. That's why insertion sort, even in academia, people don't really use it very often because of the average case and worst case is ON squared. But in some cases, insertion sort is actually very efficient. It's even more efficient than merge sort and quicksort or other advanced or heap sort. By very small, the number is usually below 10. So if they are like below 10 or like say 7 or 8 or 9 numbers that needed to be sorted, insertion sort usually is very, very fast. And actually for some of the more advanced algorithms, for example, quicksort, when they do divide and conquer, and when they divide to the very minimum level, for example, the elements that the range that needed to be sorted is less than 10, at that moment, quicksort or merge sort, they apply insertion sort because it's very fast. Alright, that's all that I have for insertion sort. If you think this video does help you understand how insertion sort works, just do me a favor and hit the like button. I really appreciate it. That means a lot to me. And don't forget to subscribe to my channel. This channel is dedicated to provide high quality computer science, education, and technology videos. That's it for today's video. I'll see you guys in the next one.